we have to make sure that we know about the Oracle database and instance architecture. We have to make sure that our understanding of the architecture is perhaps greater than you have already. Maybe not, but we'll see and make sure we're all on the same page of the manual as it were. What actually happens when we do DML? What happens in memory and on disk when we issue a commit? That's essential background knowledge to understand how instance recovery and media recovery works. Right, definition. Oh, by the way, the recording of this course is running, so if you're interested, if you want to go, we have to be very precise with our terminology here. Instance recovery, media recovery. The Oracle instance is background processes and memory structures. The database is files on disk. Don't confuse the two. And Oracle's terminology, instance recovery is necessary after a problem with the instance, i.e. the instance crashed. Media recovery is necessary after damage to the database, damage to physical files. So that's our terminology. We're going to be precise on it. I'm going to pick you up on it if you ever get it wrong. Then we'll move on to user and server managed backup techniques. Basic terminology here. What Oracle calls user managed backup, is backup done with SQL Plus and operating system commands. Server managed backup means RMAN, Recovery Manager. That's the terminology there. And of course, for this week, we're using almost exclusively server managed backup techniques. Though there are times when we'll be using user managed techniques, we have to be familiar with them. Now, you might not use them in your current job, but you could be fired tomorrow and go to another site where that's all they use. So most of the time will be RMAN, server managed backup, but we'll have a quick look at user managed backup techniques as well. And the review of the instance and database architecture, that will take us back to the recovery mechanisms. So that's our agenda for this chapter. Now, this is you need to be aware of what you're trying to achieve with your backup and recovery strategy. The fundamental point here is that there is no such thing as right or wrong, no such thing as good or bad. All there is with backup and recovery is whether you as DBAs are conforming to the standards agreed with your users. There's no right or wrong. There's no rule that says you must be able to recover the database with loss of no more than 5 minutes work. There's only what have you agreed with your users and can you do it? That's what you've got to hang on to. Documentation is vital. You need a service level agreement that says what loss of data is appropriate, what downtime is appropriate, and it's got to be agreed. And that takes you to the sort of problems you might hit. Your service level agreement would need to say what would happen if we lost a file system? What would happen if a database server exploded or someone stole it and sold it on eBay? What must happen if we lose connectivity to a data center? You have to document the type of problem you might have to deal with and agree with your users what downtime or what data loss is acceptable in those circumstances. Always remember that. There's no right or wrong.
So this is Dave. Pardon me. Do you guys know what or do you have standards for and service level agreements for recovery? Do you know what the standards are or service level agreements are in your shop?
Yes, but they vary. So depending on if it's a high availability system versus we have lower systems. So it depends on what system it is.
Got it. That makes a lot of sense. Very good. Well, it's good to hear that those SLAs.
And make sure it's properly documented. For example, you can configure the Oracle environment for 0 data loss and 0 downtime under any circumstances. And you talk to your users, and they will say, "Oh, this database is really important. 0 data loss, 0 downtime." You go back to them and say, "Yeah, we can do that. And it'll cost you this much." And at that point, all of a sudden, the requirement becomes less stringent. and you're told, oh yeah, well maybe we could stand a couple of hours downtime. But if anything goes wrong and you have those 2 hours downtime, heaven help you, if it isn't documented, that was what you had agreed would be the result.
Where
VNC is not connected.
yeah, it's not up there.
Oh, it's not?
No.
Oh, so you guys not connected to him?
I'm sorry, Dwayne just was trying to get into the VNC part, but we're not there yet.
Okay.
So Rob is just letting him know we're not there yet.
Cool, I've made a note. We'll make sure we get it all working at the end of this chapter.
Okay.
Okay. This is just a brief mention of what Oracle would like you to use for high availability. There's RAC and DataGuard, and these, of course, are the flagship products. I know you said, Tia, that you aren't using either of these. Fine, no need to talk about them any further. Yeah. Other than to say
I don't
RAC
know.
theoretically
Hold on a
100%
second.
uptime.
Well, we are using RAC on one of our systems,
Are you
Oh,
using
yeah.
RAC?
on Cerner.
Sure.
Okay.
Well, that might be where we're
That's
going.
interesting.
We might be adding some RAC later. Dwayne is working a little bit with it on one of his systems. So
That's interesting.
you can speak to it if you want to. It will probably be coming up later. We might be moving to it towards in other systems coming up, but we're not there yet.
If relevant at any stages, I'll mention one or two RAC-specific points then when we get to the appropriate
Okay.
areas. All I'll say now is that with RAC, when you're implementing RAC, make absolutely sure you know why. Absolutely sure. For example, typically RAC is used for high availability, scalability, or performance. High availability, yes, you can lose a node and the database remains open. That's what Oracle calls 100% uptime. But never forget, if you do lose a node, there will be a period of greatly reduced service. If you lose a node, the entire cluster will freeze. Maybe for only a couple of seconds, but if it's a big, big cluster and you've got 500 gigabyte SGAs, you're going to notice. It'll be a fair few minutes. So RAC delivers 100% uptime, but there is in fact, in the event of problems, a short period when the system is not available. So Oracle's definition of 100% uptime may not be what your users think of. The second reason, scalability. RAC will deliver that if the entire environment is scalable. Performance. RAC and performance is highly questionable and may need a lot of tuning. So that's all I'll say now. RAC is principally high availability, scalability, and performance. But all three of those elements, you need to be aware of how your software will actually react. It may not be quite what the Oracle salesman would tell you. Then we've got DataGuard. That's zero data loss. No compromise there. You can configure DataGuard to give you absolutely zero data loss. But you cannot configure it to give you zero downtime. You may be able to get the downtime down to single-digit minutes, but it's always going to be a certain amount of downtime. Add the two together, and you've got what Oracle might as well call maximum license revenue architecture. You've got RAC plus DataGuard. That can be quite complex to set up. Moving on from there are replication solutions. Oracle is de-emphasizing replication like there's no tomorrow. In release 12.2, advanced replication is actually de-supported. Streams has been deprecated since 12.1. Why have they done that to advanced replication and streams? Because they want you to buy Golden Gate licenses. So Golden Gate is now Oracle's premium product for replication systems. If you're enabling protection that way, Oracle really doesn't want you to do it with these license-free options anymore. Okay. The only license-free replication option you still have is materialized view replication. So moving forward, we have to move replication out of the high availability solution unless you go for Golden Gate.
John, I just find that amazing because of the amount of investment people have in streams and advanced replication.
I think it's extraordinary. Streams, in my opinion, will never go, by the way. If you're using streams at your site, I do not think they will ever de-support streams. Why do I say that? Because streams is the underlying technology for DataGuard logical standby. So I can't see it ever being de-supported. Deprecated just means they don't want you to use it. De-supported is a different matter.
Okay.
So Dwayne or Tia, do you guys use string-to replication?
We're not doing any replication right now.
Okay.
Moving forward, you've got to think about it's things like getting data from transaction processing systems into data warehouse systems, that sort of things where replication can be wonderful. And the options are getting narrower moving forward. Then, of course, there's media damage. You don't use ASM at the moment, do you? But
I'm sorry, use what?
Do you use ASM at the moment?
Yes.
You do. Excellent. And you'll be using it on your rack environments almost certainly. Okay, our classroom environments, we just use disk file system. We use file systems rather than ASM. But everything we can do on disk will be relevant to ASM as well. And if it's of interest, I can give you a few examples of running RMAN on ASM as well. So, now we come to our assumed knowledge. Instance failure. Instance failure means damage to the database instance, processes, and memory structures. Database, files on disk. Well, I've just put on this slide a few things that can cause instance failure. Aura 600s, of course, not mentioned, or bugs, I suppose. But when you have an instance failure, you destroy the memory structures, you kill the background processes. At that point, the database is corrupted. It is corrupted. Why? Because of the way Oracle works. Your sessions are always working in memory. You're copying blocks from data files into database buffer cache. And in the database buffer cache, you're doing your DML. You're doing your processing. And eventually, data is written back to disk. Now, we've got two significant disk structures here. We've got the data files, and we've got the online redo log files. Now, if you execute a transaction, or even a select statement, your server process will search the buffer cache for the blocks it wants to read, and if they're already in memory, great. Proceed to execute the statement. If the blocks are not on memory, your server process will read them from disk into the database buffer cache. If you're running a select statement, the projected columns of the selected rows then transferred to your session and processing continues. If it's a DML statement, you've got to write to the buffer cache. Now, we need to have a precise understanding of what happens when you execute those DMLs. And that we'll cover in the next slide. Because following instance failure, the database is corrupted. Why? Because you're working in memory and the write to disk is asynchronous. That means committed transactions may be missing from the database. Potentially, even more confusing, uncommitted work may have been written to the database. So, how does that happen? Because of the checkpointing and commit processing mechanism. Now, processes. Database writer copies dirty blocks to disk. Now, I'm going to try to draw a diagram at this point, and we'll see how well it works. So, what I want to do is just zoom that a bit. There we go. What I want to do is sketch out how Oracle executes DML.
At the go-to meeting.
The go-to meeting.
So,
And the email.
if this is your user, he's running a user process. Now, your user process might be SQL+, might be something written in Java running on an application server, could be forms, could be anything. Your user process logs onto the database instance via a server process. A server process. Okay? That's meant to say the word server, a server process. Then here we've got the instance in memory. We have a big block of shared memory, the system global area. Right, The system global area consists of a number of data structures. There are, let's see, there are 3 data structures that will always exist in the system global area, and there are 3 of you. That's convenient, isn't it?
Mm-hmm.
Can you give me the 3 required structures of the system global area? What shared memory structures will every instance have? I've already mentioned one of them.
DB.
DB is a good start. Memory structures at this point. Where does the DB writer write from? What memory structure does it read? It's the database buffer.
Cache?
Got it.
Cache?
Terminology. Database buffer cache. The database buffer cache is our work area for SQL. And there are 2 other memory structures you will always have. Every database instance will always have
The redo log? Is that
the
a
redo log buffer.
buffer?
The redo log buffer. We will always have the redo log buffer. And the third one that doesn't really matter is the shared pool. But sorry, it does matter. It doesn't matter right now, the shared pool. So these are the 3 required structures: database buffer cache, shared pool, log buffer. Right, shared pool, forget about it for now. It's used just as a cache for recently executed SQL statements and a load of other stuff. Doesn't matter for our discussion at the moment. Database buffer cache and log buffer matter a lot. So that's our instance. The session is the user process talking to a server process. The SGA, the instance, the database buffer cache, shared pool, and log buffer, plus a bunch of background processes. You've already mentioned the database writer. The other critical background process at this point is the log writer, the LGWR. Then we have the database on disk. So down here on disk, ASM disk groups or whatever it is, I've got the database. Right, every database will have 3 file types. And once again, there are 3 of you. So what 3 file types will we always have?
You went off the screen.
If you hover down below the bottom edge, it'll.
I could go down?
Yeah.
Okay. Continue.
Okay. That's my attempt to draw a disk. Okay, Tia, what file types do you get in an Oracle database? Robert, Dwayne, give me a file type.
Oh. We can't think. Our Oracle's not in front of us.
You will always have a set of data files. Hundreds, thousands of them, terabytes big.
So that's connected. Those are essentially, another level of from the table space. So when you create a table space, there are 1 or more data files connected to that table space.
Exactly. Let's take a look at the database I've got here. Taking a look at what I've got here. This is just a little Windows database. So if we look at my SGA, show SGA, whoops, spelling mistake and all. My system global area has a log buffer, database buffer cache, and that lot basically is my shared pool. So shared pool, buffer cache, log buffer. Then my files. Data files I've already put on my diagram here. So if we look at the structures there, if I select star from $, table space, my table space structures, I've got a total of 6 table spaces, and there's the join column, TS hash, that's my join column to $, data file. So there are my 6 table spaces. TS hash is the join column to $, data file, and there's my data files, each of which, of course, selects TS hash name from $, data file, and there's my 5 data files. It's not showing the temp file because the file for my temporary table space is managed differently. So we've always got our data files. Other file types, we've got the database writer manages the data files. The log writer That's my online log files.
The log files.
My online log files. I'm being really precise in the terminology here because my archive log files are, of course, a bit different. And then the third disk-based structure is, of course, the control file. And the control file I'm really not bothered with at this point.
Right.
So that's the Oracle architecture in a nutshell. A session is a user process talking to a server process. An instance is that big block of shared memory in the SGA and a whole bunch of background processes. I've only mentioned 2 of them at the moment. Then the database is files on disk. Data files, online log files, control files. So that then is the physical structures. How do we actually use them? Come back to the slide. We've got to get data into memory and then write it back to the database. So what I'm going to do is execute a fairly basic bit of SQL. If I do this, say, update emp set, update emp set sal equal sal plus 1, where ename equals king. Okay, doesn't work because I'm in the wrong schema. Connect Scott Tiger. Right. Okay. What happens when I run that statement? Well, what we've got to do is find which block of which data file contains Mr. King's record, or row, I should say, which block has his row, because somewhere on disk in the data files, there's a block here that contains King's data. There's a block. And it's got a bunch of rows, including the one for Mr. King. That's meant to be a K for King. Now, if that block has already been copied into buffer cache, great. If it hasn't, my server process goes to the data file, reads that block, and copies it into memory. So server processes read the data files, and they copy into memory. So up here, I've got a copy of the block that says Mr. King's salary is whatever it is, 5,000 or something. This is DML, and we're talking a relational database. That means we have to have undo data from our undo segments. If I'm wasting time on stuff you know backwards, say so. If anything isn't completely clear, say so. But whenever we update a block, a row, we have to write the previous version of the data to an undo segment. So my server process goes to disk, finds a copy, a block of an undo segment, which is available for use, and it copies that block of undo segments into memory, if it isn't there already. So this here is my block of table data, so Mr. King's salary is 5, and this is my block of undo data. My statement was update. The way Oracle handles DML is before you write to blocks in buffer cache, you write the change vectors you are going to apply to the log buffer. So I'm going to do my DML in red. So black is the original version of the data. An undo block that's empty, and the table block that says Mr. King's salary is 5. I'm going to execute that statement. So the first thing my session does, well, we've got the data in memory, we write to the log buffer the change vectors we are going to apply. Well, we are going to update Mr. King's salary from 5 to 6. That's meant to be 5 and an arrow going to 6. We're going to update his salary from 5 to 6 in the row, and we're going to write the old version of his salary, which was 5, to the undo block. So that's 2 changes. A change to the table, that his salary is now 6, and a change to the undo block, saying his salary was 5. Having written those change vectors, we can make the change. We update his salary in the table to 6. We write the old version of his salary to the undo block as 5. The DML is now executed. What's on disk? No change.
So let me just interject, John. So to the students, this is maybe the first mention today of undo, and what is the undo block used for? Why do we hold that 5, that original number?
In case you have to roll back.
Precisely. And could you identify who said that? Because I'm just trying to get comfortable with whose names are speaking. Obviously, I know when T is speaking, but between Dwayne and Robert, who was that?
That was Dwayne.
Thank you very much, Dwayne. Excellent. Yep, rollback, in case you need to roll back. And John is going into the details here. And once again, if you guys know these details, inside and out, just let us know for sure, because these details are going to be critical, because depending on where a failure occurs and when a failure occurs in your database, knowing this will assist you in what you have to do to recover the database, and that will obviously become clear as we go through the course.
You can see here, the rollback has been done in this query here. King's salary is on the old value of 5,000, and that, of course, is rollback for read consistency purposes. But if the database crashes at this point, or I issue a rollback command, such as rollback, boom, then, of course, we have backed out the change, and we're back where we were before. So rollback because of failure, which I haven't demonstrated, rollback because I requested rollback, or rollback to provide read consistency. So it's always going to be change vectors to undo and change vectors to the table. And either way, what's on disk? Nothing. Come to the slide. Checkpointing commit processing. Database writer is responsible for copying changed buffers from buffer cache back down to the data files. Eventually, we're going to copy those changed blocks down. Log writer is responsible for copying change vectors from the log buffer into the online log files. When do they do this writing? Database writer writes with a lazy algorithm, as little as possible, as rarely as possible. The idea is that disk I/O is bad for performance. So you only ever write the data files if you have to. And it's a bit more complex on this and it varies from release to release. But in general, these are the 3 reasons for database writer writing buffers to disk. Right now, I've got 2 dirty buffers. My buffer cache might have 1 million buffers. If I'm using 8K buffers, and my buffer cache is 8 gigabytes, that gives me 1 million buffers of 8K each. Of those 1 million buffers, at any given moment, how many are dirty? Well, in my diagram here, 2 of them. Of my 1 million buffers, 2 have been changed. Now, eventually, database writer is going to copy the change buffers to disk, but it writes as few as it can get away with. It will write if it thinks there are too many dirty buffers. What's too many? Internally tuned. But of my 1 million buffers, perhaps half of them are dirty. Database writer might think, oh, I better copy some to disk. No free buffers. A database server process, a session, wants to copy a block into memory, and all it's finding is dirty buffers. It will tell database writer, copy some of them to disk, so they become free and available for use. That doesn't actually mean no free buffers, in terms of there are no free buffers. It means a session couldn't find a free buffer quickly enough. That also will force database writer to clean the cache, copy some buffers to disk, and every 3 seconds will do so anyway. But there might be 100,000 dirty buffers. Database writer might write just 500. It writes as few as it can get away with, because there's no point in writing data to disk if you don't have to. The data might be needed again, so keep it in memory. Log writer, by contrast, writes in a very aggressive algorithm. It's streaming change vectors to disk in very nearly real time. And when you say commit, it is real time. But in any case, log writer writes in nearly real time anyway. Now, that 1/3 full trigger, your log buffer is only a few megabytes. That 1/3 full trigger is firing continuously as you generate redo. So, already, in the few seconds we've been talking, those change vectors will already be in the buffer cache. Sorry, in the log files. So already on disk, we'll have the fact that King's record was updated to 6, and the undo segment has the old salary of 5. Those change vectors will be on disk already. Has database writer written those blocks to disk? Almost certainly not. Now, what happens then when I do say commit? When I finally do issue a commit call, my server process says, well, my user process says commit. The server process puts a commit record into the log buffer. The commit record into the log buffer, and the server process hangs while the log writer flushes the log buffer to disk. So even if those changes aren't on disk already, my session process will hang while log writer writes it. And only when that write of the log buffer to disk is completed is commit complete returned to my session. What does database writer do when you say commit? Absolutely nothing. Absolutely nothing. And if any of you work with SQL Server, that's a big change. You know, some other third-party database products write the data blocks to disk on commit. Oracle doesn't. Now, why should I write that block to disk? Yeah.
Let's take a pause. So a couple of things are happening on my screen I'd like to clarify. I'm getting some flashing. And to the students, are you guys seeing some flashing?
Yeah.
So John, it appears what's happening is like the imaging software seems to want to be at the top, and it's not flashing as they're just happening now. So I don't know if you're moving your mouse.
I did. I moved the mouse.
So as we speak, the flash is not occurring, but it seems that it always wants to be on top. Perhaps, maybe that's why. And when you move in, like let's say the SQL Plus screen to cover a portion of that, while you're writing in the SQL Plus screen, there's no flashing. It's starting to flash now. But if you take there are times, perhaps when you take the focus off of the SQL Plus screen, it starts to flash, as if something wants to be on top.
Oh, okay, because I need to be a lot more careful. What I'll do then is I can use the minimize and maximize instead.
I'm sort of guessing at the reason, but...
Yep. I'll minimize and maximize rather than keep all the windows open.
Okay, and to the students, so we've got to sort of a critical point in the execution of this DML, of this update and this commit. And in my view, understanding what is just about to be explained is one of the very critical moments of the course, because it really does come into play. So we've got a commit executed, which John has explained that the commit forces the log writer to write your change and the commit record to the log file. So it's on a file, it's on disk. It's quote unquote permanent, of course, unless that disk fails. But what John has also said is that the database writer has not written the dirty buffer to the data file. So you've got an inconsistency, and you want to be sure that you've got that understood very well. You've got a commit record written out with the update to the log file, but the data file has not yet been updated. So if somebody unplugged your server right now, if the instance crashed, you've got a change that's been committed, but the database has not been updated. Back to you, John.
That's the concept of consistency. The database right now is inconsistent. It is missing a committed transaction. Because when I issued my commit up here, my session hanged until the log writer flushed the log buffer to disk, and then we have commits, the commit record as well down there. That the database is inconsistent, it's out of date. Does that matter? No, because in memory, we've got the real-time information. The SGA knows what's committed and what isn't. But if the database failed, we've got a corrupted database because it's missing a committed transaction. If it does fail, we issue a startup, and what will happen then? Instance recovery. In mount mode, the database will realize that this is inconsistent because the database crashed, all the file headers were out of sync, all sorts of stuff is wrong, is obvious. And what Oracle will do, what Oracle will do for instance recovery is replay the change vectors in the online log. It will go to the online log file, find that change vector that refers to that block, copy that block into memory, and apply the change. The second vector applies to the undo block, which is empty. Bring that into memory, apply the change. So instance recovery reinstantiates the transaction, and then as it works its way up through the online log, it finds the commit record, okay, flag it as permanent. If it did not find a commit record, i.e. the change was not committed, that would trigger a rollback, because the instance recovery recovers both the transactional change to the rows and the change to the undo segments. So we always have the capability to reinstantiate both committed and uncommitted work, but we also reinstantiate the undo segment so we can roll back the uncommitted work. So forward recovery rebuilds work committed or not, and then you roll back the uncommitted work. Going back to the slide, that's how it functions and why. Database writer writes in a lazy algorithm, is always behind. Log writer writes in very nearly real time, and uncommitted is real time. So database writer is always behind. Always behind. So in the event of a crash, your database is corrupted. Instance recovery rebuilds the cache into the state it was in before the crash. It uses the online logs to rebuild the cache between mount and open. It looks at the online log, SMON does, works out the changes that need to be applied, brings blocks into cache, applies the changes, and at that point, database writer checkpoints them to disk. So any data that wasn't written to disk is in fact written to disk during the instance recovery. And the recovery is both data segments, i.e. index and tables, and undo segments. So the forward recovery reinstantiates everything, and after opening, we roll back what hasn't been committed. And that's our instance recovery mechanism. It's totally automatic. You couldn't stop it, even if you wanted to.
Mm-hmm.
Now, the forward recovery is based on the online logs. What if the online log were damaged? What do you think would happen then when you try to start up the database?
It wouldn't be able to continue, would it? It would give you an error
That's
that
exactly
couldn't
it.
find the file?
That's exactly it. The error will depend on the nature of the damage. But whatever it is, you can never open a database if your current online log file is damaged. Because, as far as Oracle is concerned, at the time of the crash, the database will have been corrupted. It might have been missing uncommitted changes, because database writer is writing behind. It might be storing committed changes. How would that be? Because the algorithm database writer used in the previous slide, this algorithm for what to write is not related to commit processing at all. It will write data committed or not if it has to. So after a crash, the database will be corrupted. And unless, next slide, this rebuild can succeed, Oracle will never let you open the database again. You have to do incomplete recovery. So
what is one of the things I'm sorry, John, what is one of the things that we as DBAs should do in the architecting of our database to reduce the chance that our online log prevents us from opening the database? You know, we have a disk failure on a log file. What should we do in the build of the database to reduce the chances that a single log file causes that?
Multiple sets.
Say again, T. I couldn't hear you.
I said that's why we have multiple sets and we back them up.
Yeah, you bet. We multiplex, mirror the log files. Thank you. Excellent.
that is vital. So in my little database here, I've got 3 log file groups, and each group has 2 members. So just to make sure we know about the relational structure here, we have at least 2 groups, so Oracle can switch between them. I've got 3, and vdollar-log, 1 row per log file group. And we join that to vdollar-log file. And you join column, group hash. So I've got 3 groups, each of 2 members, and this will show me the actual members. So call member, format A80. Select star from vdollar-log file, set len 200, stretch that out a bit, and there we see my groups each consist of 2 members. And that, of course, is vital. And your service level agreements, again, will have statements in them, such as every production database will have 5 online log file groups, and each group will have at least 2 members. If you don't have that sort of thing in your service level agreement, perhaps it should be added. Yeah. So, the forward recovery, there's not much you can do about it. There's a bit of tuning. We'll talk about that later on, perhaps. How long does it take? Well, it depends on the size of your buffer cache, how much recovery is needed. There are ways to tune it. I'll show you the view right now in case you're interested. If you look at vdollar instance recovery, this is the view. And at this precise moment, if my database crashed, there will be that many reads, writes required on the data files. We would have to read that many blocks of redo, and it would take approximately that many seconds. MTTR, mean time to recover. So if my database instance crashed right now, the recovery time would be basically 33 seconds. There will be a small amount of I/O needed, a small amount of redo needed, and it would take about half a minute. So the recover, but run that query in your production systems, and you may be quite horrified of what that turns out to be. There are ways to tune it down, but that's the length of time to do the recovery. Instant recovery. Transaction recovery then, as I described or tried to describe, the instance recovery process reinstates all work committed or not, including the undo changes. And then it will roll back the uncommitted work afterwards. How long that takes really doesn't matter, because the database is open at that point. Now, people will sometimes even slow that down so that the rollback doesn't take up too many resources. Then we move on to media recovery and our first tea break. Now, media recovery is damage to the database. Right. Damage to your files. Data files, temp files, online log files, control file. What does that damage mean? Well, maybe files have been disappeared, accidentally deleted, trashed for some reason, truncated by the operating system. Or maybe it's some form of corruption, or maybe it's an issue with your storage systems, and you've lost whole file systems or disk groups. And that is not automatic at all, and that's the bulk of our 5 days together. The recovery, well, you have to work out which files are damaged, take appropriate action, which will nearly always be a restore. Restore the files from backup, and then apply redo to make the restored file consistent with the rest of the database. Apply all the change vectors from archive redo logs to bring it forward in time. Now, techniques for backup. User managed, the old-fashioned way. Some sites still have to do it. SQL Plus and operating system services, not much automation there at all. RMAN Recovery Manager is the clever way to do it. Now, let me just check. Do you use RMAN on all your databases, or do you still have systems using user-managed techniques?
We have both going on. We have some.
Right.
There are only not many using RM. They're mostly using the manual.
Right. I remember you said when we. Right. You said last week you normally do cold backups and copy things, don't you?
Right. But we do have a few running RMAN.
Right.
We do have a few, but not all of them. They should all start running RMAN. We don't have them all running.
Okay, if you're using user-managed backups, the simplest way to do it is just to shut down the entire database and copy it. You can do hot or open backups using user-managed facilities. And if you would like to, tell me probably tomorrow, and we'll go through the user-managed hot backup technique. So tell me tomorrow if that will be of interest as your current method of user-managed backup.
Yeah, I don't think we need to do that. We're pretty much got that covered.
That's cool. That's cool.
We'll do hot ones. I always do.
We always do cold backups. We shut down the database, we copy everything over, and bring it back up.
As long as it really is shut down, that's a valid backup. If something goes wrong with your scripts and it's open while you do that, the backup is useless.
Right, we do scripts and we keep a log of everything that's going on, and we test them. So we test them, so we know our cold backups are working. It's just that it's an outdated technique.
Cool. Okay, we won't spend time then on user-managed hot backups unless there's some reason to, because what we'll be doing is server-managed backups with RMAN. There's a lot of automation once you've written the scripts, and we'll go through loads of different scripts. A lot of automation. And there's all sorts of clever stuff you can do as well. Now, that then was our introduction to the architecture. The architectural stuff we covered, including in particular what happens when you do DML, we have to have a rock-solid understanding of what's going on in memory, what's going on disk, why files are inconsistent, what's necessary to make them consistent. We must have a full understanding of that. And if any of that wasn't clear, think about it over tea break and tell me, and we'll work it out together. Right. But the architectural background, we need to have a full understanding of what that's all about. Okay then, what we'll see then throughout the rest of this week is that if configured correctly, we can have zero data loss. Zero downtime? Maybe. Depends on the nature of the problem. Depends on the nature of the problem. No, but without RAC, you're never going to get zero downtime in all circumstances. And even with RAC, remember, there is that issue of is it really zero downtime, given the failover capability from instance to instance. If you'd like any help, if you're interested in any help in configuring that, by the way, I love working with RAC. I really enjoy it. So we'll see zero data loss is possible, not zero downtime, depending on the nature of the problem. User-managed backups, you won't be needing to use them, but they are still supported, of course, and we're going to be using RMAN throughout.